Hi, my name is Hugo Richard. I'm a PhD student at University Paris-Saclay. I'm in the parietal team and my supervisor is Bertrand Thirion. Today I'll present my work about modeling shared response via MultiView ICA. This is a joint work with Luigi Gresley, Aapo Ivarinen, Bertrand Thirion, Alexandre Granfort and Pierre Ablin. First, let us focus on this problem where two sources are emitting a signal that is recorded by two sensors. This can be seen as a model of magnetoencephalography, where magnetometers record the signal emitted by activating neurons. Because propagation time can be neglected, the signal recorded by the sensors can be seen as a linear mixture of the signal emitted by the sources. S is a vector of sources that are assumed to be independent. X are the recordings, and A describes how the recordings are modeled as a linear mixture of the sources. At first sight, this model may seem ill-defined, because if we permute two sources and the corresponding columns in A, we'll get another set of sources, S', and another mixing matrix, A', that describes X just as well. Similarly, if we take one source and multiply it by some constant, and take the corresponding column in A and divide it by the same constant, we'll get another matrix, A', and another set of sources, S', that describes X as well as A and S. However, if we assume that at most one source follows a Gaussian distribution, then the previously described scale and permutation indeterminacies are the only one. This is important because it tells you that ICA is a well-defined model up to trivial indeterminacies. Now, let us consider the more general model, where we record information about two subjects. They share the same sources, S, but have different mixing matrices, A1 and A2, and different noises, N1 and N2. We'll assume, like before, that at most one source is Gaussian. The shared sources model shared cognitive processes. The different mixing matrices account for the different spatial topographies of each subject, and the different noises model artifacts, such as the one caused by head movements. A natural solution to this is just to use ICA for each subject independently. The recovered sources will differ in permutation and scaling. A simple solution is just to scale the sources so that they have variance 1 and use the Hungarian algorithm to align the sources across subjects. Then the estimate of the common source can be seen as the mean of subject-specific sources. Another approach is to stack the recordings of subject 1 and subject 2 into a vector X. We then extract the first k principal components of X, yielding a vector X-red that has the same dimension as the subject-specific recordings. We perform an ICA on X-red and obtain the common sources S. The problem with the approaches previously described is that they do not optimize the proper likelihood. Therefore, they do not benefit from the advantages of such estimators like statistical efficiency. Let me introduce MultiView ICA. MultiView ICA is a model with a closed-form likelihood and comes with a fast optimization algorithm. We have theoretical guarantees that our model is robust to misspecification of hyperparameters, and experimentally we see that our model outperforms all other group-ICA methods on various experiments involving two different neuroimaging modalities. Our model sees the data recorded by the sensors as a linear combination of shared independent sources plus noise. Importantly, the noise is on the sources and not on the sensors. Now, our model can just be seen as a special case of noisy ICA, but let me try to convince you that this special case actually allows us to solve problems that are difficult to solve for general noisy ICA. So we now focus on a similar model as ours, but with noise on the sensor side. As we see, the likelihood involves an integral, but the integral does not factorize. This makes the problem difficult and intractable in general. In contrast, our model has a closed-form likelihood. Like in noisy ICA, the likelihood involves an integral over the sources. We can factorize the first term of the integral because the subjects are independent given the sources. The second term we can factorize because the sources are assumed to be independent. We then perform a change of variable where xi is replaced by wixi minus s, where wi is the unmixing matrix, which is the inverse of the mixing matrix. We then make use of the Gaussian assumption of the noise, and we can see that the integral factorizes. It only depends on the product of one-dimensional integrals. Further computations available in our paper show that these one-dimensional integrals have a simple expression involving the initial densities smoothed with a Gaussian kernel. We then write the likelihood, which is minus log of p of x, and it is simple to evaluate, and interestingly, when m equals 1, we recover the usual likelihood of maximum likelihood ICA. Now that we have found the likelihood, we need to minimize it. To do so, we perform an alternate quasi-Newton. We first fix all unmixing matrices Wi except 1. And for the one that is not fixed, we perform a quasi-Newton step. In our case, the quasi-Newton step takes the form of a multiplicative update that involves a direction which depends on the inverse of the Hessian. The exact Hessian is block diagonal, but each block is too big to obtain a fast algorithm. We therefore resort to an approximation that is exact when the unmixed data are uncorrelated. This is not a big approximation, as the unmixed data are estimates of the sources that are assumed to be independent. With our approximation, the direction is super fast to compute and therefore it yields a fast algorithm. Let us now focus on our theoretical contribution. We first show that MultiView ICA is identifiable. We'll take the usual assumptions in ICA and assume that at most one source is Gaussian, and that the sources are independent. Then we show that there exists one scale and permutation matrix that is global and does not depend on the subject, such as we can recover the correct mixing matrices. Our second contribution is about the noise level parameter sigma. We first make a technical assumption on the densities that is checked in practice, and then we assume that the data follows the model but with a different noise level than the one in the model, and a different density than the one specified in the model. Even though we do not use the correct density nor the correct noise level, the algorithm is still able to find an interesting solution because the correct mixing matrices, up to scaling, are a stationary point of the loss of MultiView ICA. We now discuss our experimental results. We've made this synthetic experiment where we generate data according to the Laplace density and with various levels of noise from 1-2 to 10. And then we fit our model with a different density than the one used to generate the data and a noise level that is always fixed to 1. What we see is our model is uniformly better than other approaches. We can actually see in practice that our model is robust to a bad setting of hyperparameters. A second experiment involves MEG phantom data collected using a realistic hedge phantom, which is a plastic device mimicking real electrical brain sources. 8 current dipoles positioned at different collocations can be switched on and off. We view each dipole as a subject, and an epoch corresponds to 3 seconds of MEG signal. We choose 2 to 16 epochs at random and concatenate them in the time dimension. We apply algorithms on this data to extract 20 shared sources. As we know the true source, we can compute the reconstruction error of each source as the squared norm of the difference between the estimated source and the true source. We only retain the source of minimal error, and what we see is that MultiView ICA requires fewer epochs to correctly recover the true source. Let us now consider another experiment on fMRI data, where subjects are exposed to a naturalistic stimuli such as movie watching. 80% of the runs are used to learn the unmixing matrices, and in the 20% left out data, we apply the unmixing matrices and recover the source, and we select a 9 time frame time segments in the source of a left out subject, and compute its correlation with all possible 9 time frame time segments in the average response of other subjects, excluding partially overlapping time segments. And the time segment is said to be correctly classified if the correlation is maximum when the time segments are overlapping. MultiView ICA yields a consistent and substantial improvement in accuracy compared to other methods on the full datasets. So we've seen that MultiView ICA is a principal approach to perform group-ICA. It has appealing theoretical properties and yields better results in practice. We've made so much more experiments than this. I'll leave you with this beautiful image where we've localized and identified, using MultiView ICA, the common source to the MEG data of 200 subjects exposed to an audiovisual stimuli. Thanks for listening and have a good day.